We're going to continue on here. We've rolled into some chapter. 14 sounds like a good chapter. Remember, 14 here does contain a lot of stuff, especially in the book we're using. You just put like everything into 14. It just keeps going on and on and on. So the first part of 14, as we started talking about last time, is about acids and bases. Actually, the whole chapter is really about that. But then we will roll into some other things like titrations and buffers, I believe is in this chapter, hydrolysis of salts as well. So again, there is a lot going on in this chapter. And as we talked about last time, this chapter and the one after it is really, again, the two that give people a really difficult time in this class. You really do need to think about the conceptual aspect of what's going on as we go through these things. So it will help you definitely with the calculation part. So we opened up with talking about acids and bases, I think, in this chapter last time. And remember, your basic definition of an acid is something that's able to produce H+ ions in solution. Remember, in acid-base chemistry, H+ and H3O+ are essentially the same thing. You just get H+ if you really don't include water in your equation. If you include water in your equation, you get H+. A base, on the other hand, right, is something that can produce hydroxide in solution. And it's a free H+ or free hydroxide that gets produced, which is what makes something an acid or a base, is the ability to do that. A more general sort of definition of acid and bases is the Bronsted-Lowry definition, which is what a lot of people use to define acid and bases. Bronsted-Lowry acid is a proton donor. And remember, a proton is H+, so that is another sort of name referred to it. A base is a proton acceptor. And remember that the consequences, sort of Bronsted-Lowry definition of acids and bases, is when we have sort of reaction of an acid and base, it will create basically partners on the other side. And the partners on the other side is the conjugate acid and the conjugate base. And the relationship between these two guys is the acid on the left-hand side is related to the conjugate base on the right-hand side, and the base on the left-hand side is related to the conjugate acid on the right-hand side. Also remember that we basically find those guys on that side of the arrow. So acid and bases on the left-hand side, our conjugate partners are typically on the right-hand side. The major difference between them, and really the only difference that you could have between them, is exactly this. It is one H+ difference is the only difference that there can be in order for those guys to be pairs. So since the acid will donate an H+, the conjugate base will have one less H+ as it goes to the other side. And the base, since it will accept the H+, the conjugate acid will have one more H+ as it goes to the other side. In addition, it is not just the H is either being given away or being added. The plus makes a difference on the overall charge of the guy. So if you lose a positive charge, you become one more negative. So that's sort of how that works. So that is, again, a very common mistake that people make. They kind of get the charge sort of incorrect. They just get the H on or off, but the charge is affected. Acids will lose basically hydrogens one at a time. So they do come off basically in a stepwise fashion. They don't all just drop off all at once. After that, I believe we got started talking about some Kw. Kw is the ionization constant for water. And for the most part, it is sort of a standard number that we use most of the time, which is 1 × 10⁻14. The H+ is really the acid concentration. Again, it could be exchanged for H3O+ in that formula. The OH- is the base concentration. And you really could use that to solve for one of the other concentrations. And if your H+ concentration is larger than your OH-, then it should be acidic. If the H plus concentration equals the OH minus, it would be neutral. And if the H plus concentration was less than the OH minus, then it would be basic. So this is one way at which you can figure out whether or not a solution will be acidic, basic, or neutral. You definitely, as we talked about, want to make sure you're using your exponent button when you're punching these into your calculator. Otherwise, you will find yourself sort of off in terms of your values here. I think we did this example, right? So I'm just going to scribble on this page, I think. This is the one we finished with, right? Yes, I think. Yeah, okay. So I'll scribble the rest of what we talked about last time. So we talked about pH, which is minus the log of the H plus concentration. Remember the pH scale basically runs from 0 to 7 to 14. Less than 7 is acidic. Above 7 is basic. And again, 7 here is neutral. And as you go from 7 towards 14, you become more basic. And from 7 towards 0, you become more acidic. There's also a nice relationship as well of the pOH, which is minus the log of the OH minus concentration. The name tells you what you need. pH, you need H plus. pOH, you need the OH minus to concentration. The nice thing about that is if you take the pH plus the pOH, it will equal 14. So again, that gives you a few different options as to how you can solve some of these problems, depending on the piece of information that's given to you. We also saw that if you have the pH, you could get the H plus concentration from it, and that is the inverse log of the minus pH. Again, on most people's sort of calculators, when you punch that into your calculator, it oftentimes will punch up a 10 and a caret, and then you want to do minus pH. You could also do the same thing here for pOH. It will give you the OH minus concentration, and it's the exact same calculation. It's the inverse log of the minus pOH to do that. So again, that also gives you a variety of ways to solve some of these problems where you might not have to even use KW, but you could still use KW if you wanted to, or you could use any of these other ones along the way. Any questions on any of that stuff there that we talked about? We also talked about calculators. And again, if you have a display calculator, you punch everything in this way. And if you have a non-display calculator, you pretty much punch everything in backwards to get the right answer that you need. Any questions on any of that stuff there? Okay, so I think we did this one here. We did that. So let's talk a little bit about strong electrolytes and weak electrolytes and so forth. As you may remember, an electrolyte is something that when it goes for a swim, breaks apart into ions and does what? Electrolyte will conduct electricity, right? So the presence of the ions in the solution helps complete everything. A strong electrolyte will conduct electricity really well. He used to do an experiment with a light bulb. You put the electrodes in it and the light bulb would shine very, very brightly. There are also weak electrolytes. Weak electrolytes will pretty much stay together, but they will produce a little bit of ions in solution, so they still are able to conduct electricity. Major difference, right, is like the arrows. A strong electrolyte is a one-way arrow. Everything is going off to the product side and breaking apart. The weak electrolyte are kind of reversible arrows heading in both directions, where mainly it's staying together, but you do produce a little bit of ions. So acids and bases are also strong electrolytes and weak electrolytes. And when you do have a strong electrolyte, again, 100% of what you have in that solution is just the ions. There's absolutely no units still together. Something like hydrochloric acid, it has completely broken apart. So in all these cases on the bottom, these are all some strong acids. This would break apart into H3O plus and Cl minus. This would be H3O plus and NO3 minus. This would be H3O plus and ClO4 minus and H3O plus. And really HSO4 minus. Now, and this would continue on one more step along the way. This, as we can see here, 100% what we would have would be solutions. And in this case, we would have just the ions. We could also represent a strong acid dissociating, which is really what this equation is, by simply just writing it like this, H plus and Cl minus. And once again, the H plus here and the H3O plus are equivalent to each other. Top one, we don't get H3O plus because we don't have the water in the equation. The bottom one, we do. Personally, I write it most of the time like this, but other people will write it with water. By the way, these all 100% have ions in solution, and frankly, they all produce a lot of H plus very, very quickly, which is why they are strong acids, because they basically just go for a swim and you got a bunch of H pluses floating around the solution, and that makes them a strong acid. So some strong acids: hydrochloric acid, nitric acid, perchloric acid, sulfuric acid, at least the first part is. Some other strong acids, HBr is a strong acid, HI is a strong acid. So these are all examples of some strong acids, which will 100% break apart into ions in solution. Now we do have some weak acids, which again will mainly stay together, but will break apart a little bit. So something like this would produce H3O plus and F minus, H3O plus and NO2 minus. By the way, in each of these cases, the acid is donating over the H plus. The H3O plus plus SO4 2 minus and our H3O plus and our OH minus in this case. So in these cases, pretty much what we have working in terms of what is there is really these guys is pretty much there. We do get a little bit of these guys formed. But again, a majority of what's in the solution is actually the weak acids still together. Also, you can, just like for our strong acid, you could write the equation for HF, for example, as simply HF breaking apart into H plus and F minus. So again, that's sort of an equivalent equation to this one. And again, we don't get the H3O plus there because we didn't include the water. Strong bases typically have hydroxide in them, and they come from group 1 or 2 on the periodic table, right around sodium, potassium, over to calcium, and up and down. All those guys from group 1 and group 2 that has hydroxide in the actual formula are typically strong bases. And because they're strong bases, 100% of what you would have in solution would be our product side here. And once again, we're essentially creating a lot of free OH minus really quickly. And that means that it's going to be a strong base. There's also some weak bases, and they are weak electrolytes as well. So in this case, this is going to actually accept the H plus coming this way in each of those cases. When it does, it makes HF and OH minus and HNO2 and OH minus. Right? So although a majority of what you have in solution is everybody on the left-hand side here, it is still able to produce hydroxide, not as much as, say, sodium hydroxide would produce. But because it's still able to produce hydroxide, it's still considered a base, but a much weaker base. And again, most of it is going to be F minus kind of floating around. Now, there is a very important relationship between an acid and its conjugate base and a base and its conjugate acid. And it's really the opposite relationship. So what I mean by that is if you have an acid and its partner on the other side is a conjugate base, if the original acid was a strong acid, then the conjugate base will be relatively weak. And if the original acid was a weak acid, the conjugate base will be relatively strong. And the same thing happens with our base and conjugate acid. If you had a strong base, its partner will be relatively weak. And if you had a weak base, its partner will be relatively strong. So this opposite relationship is really important when we talk about something in terms of a conjugate base or conjugate acid being strong. What that means is, as we will see shortly in this chapter, it has the potential to continue to react. So it has the potential to continue to react with water and affect the pH of the solution. So if you have a relatively strong conjugate base or conjugate acid, it can continue sort of its reaction on its own, and it will have an effect really on the pH. Happens a lot when we deal with salts, and what happens with salts and water and the hydrolysis sort of reactions. So it's important to keep those relationships in mind. Something comes from a strong acid, it's relatively weak. If something came from a weak acid, it's relatively strong, and vice versa. Obviously, are the same thing for the bases. Here's a table from your book of some of our strong acids and strong bases and their opposite relationships. So again, this is a strong acid. This is a relatively weak conjugate base. This is a weak acid. This is a relatively strong conjugate base as you go that way. All right. So not in all cases will you be given the concentration of everybody as like H plus or OH minus. Sometimes you may be given an actual formula. And if it is a formula of a strong acid or even a strong base, you can use that to help you calculate the pH. So once you try this, we have what is the pH of a nitric acid solution, which is a strong acid, and what is the pH of a barium hydroxide solution, which we will say is also a strong base. So come up with what you think it will be. We'll talk about it. Okay, let's take a look. So we have nitric acid, which is a strong acid, and it would be wise to know those strong acids that I listed on the other page. It will help you as you go through this chapter and other chapters. Because this is a strong acid, we know that it is going to basically 100% break apart into H plus and NO3 minus in this case, right? Now, since we are looking for the pH, the most important thing there for pH is which one? Yeah, it's the H plus concentration, right? Because the pH is equal to minus the log of the H plus concentration. We do know that the nitric acid is 2 times 10 to the minus 3 molar, which means the concentration of H plus in this case would be, it would be the exact same. It is a 1-to-1 relationship. So it would be 2 times 10 to the minus 3 molar. By the way, the nitrate would also be 2 times 10 to the minus 3 molar. Not that you need it. That is how solutions work, right? And ions floating around, you basically do like stoichiometry. It breaks apart into a 1-to-1, it's the same concentration, 1-to-2, 2 times concentration. If you're not sure, let me show you the long drawn out calculation here. Moles per liter of nitric acid, right? For every 1 mole of nitric acid from our equation, we get 1 mole of H plus. Moles of nitric acid cancel, gives us basically 2 times 10 to the minus 3 moles per liter of H plus. So because it's a 1-to-1 relationship, it basically is the same. And like I said, if it breaks apart into a 1-to-4, you times it by 4 and it works out the same way. All right, so now that we do have actually our H plus concentration, we will go minus the log of 2 times 10 to the minus 3. And that looks like we will end up with here minus log 2 to the minus 3 Looks like maybe a 2.7 for our pH in this case. Yeah. Acidic, basic, neutral. This one is. It is acidic, which makes sense since that's nitric acid. I would hope it would be acidic. If you got a basic, then something probably didn't go so right there with the calculation. Let's take a look at the next one, which is a strong base. So once again, here we're going to find the barium hydroxide is going to break apart into barium with a +2 charge. And we will get a couple of hydroxides here. It is in this case, because it's a base, the OH minus, that's the important thing. That will allow you to calculate the POH, which is minus the log of the OH minus concentration. So in this case, the barium hydroxide is 1.8 times 10 to the -2. What would be the concentration of hydroxide in this case? We do need to take basically 2 times 1.8 times 10 to the -2 to get the proper concentration. And that would give us like 3.6 times 10 to the -2 molar minus the log of 3.6 times 10 to the -2. Looks like it is 3.6 to the -2. And at this point, we have what we need for our POH, which would be minus the log 3.6 times 10 to the -2. Looks like maybe 1.45. That is not the pH though, right? That is just the POH. So we are needing to get to the pH. And in this case, the pH will equal 14 minus our POH, which is 1.45 minus a 14 gets you a 1256 in terms of our pH value, which does make sense because that is basic and this is a base. So that is good. Any questions on any part of that there? So once again, I would say probably the bases are the place where you might have to watch out the kind of extra coefficient there. But you do need to make sure you get the proper concentration of either H plus or OH minus in that solution in order to calculate the pH. Any questions on any of that stuff there? Okay, so let's then talk about, and here's a table, some strong acids and also some strong bases, again, in case you need it. And again, I would recommend that you kind of know these because it'll make some things a little bit easier as you go through it. And that looks like it is from your book there, so you should be able to find it. Now, that is basically strong acids and strong bases. If we have weak acids and weak bases, they are also dealt with a little bit different. Because they are weak acids or weak bases, they do not completely break apart like our strong acids and strong bases, which means they create an equilibrium. And because they create an equilibrium, that means that we get to do our favorite thing, which is ice tables. So if we have a weak acid, which is what this is, or just an acid in general, but that is acting as our acid here, it will break apart into H plus and A minus. We could write an expression of products over reactants, adding to our ever-growing list of K values. This is what is referred to as a Ka value. It is the acid dissociation constant for a weak acid. It is basically the exact same K as everything else. It is products over reactants. Once again, we do not include the water in the equilibrium, which means if we wrote it for this guy, it would look exactly the same. That would not be in there. And that would just be H3O plus instead of H plus. Now, as the Ka value increases, the strength of the weak acid also increases. So the higher the Ka value, the stronger the weak acid. Let's just sit on that word for a second there. That is the stronger the weak acid. That means it is in comparison to other weak acids, right? Not comparison to a strong acid. Why would a large K value, Ka value mean it's a stronger weak acid? What does a large K value mean? Less reactants, which by default would mean there's more products, right? When we reach equilibrium. And on the product side of a weak acid equation, what important thing do we find? You find H plus, which means the larger the Ka value, you would have more free H plus at that point in the solution. And that's pretty much your definition of an acid, right? The ability to make that H plus. So again, it would be a stronger weak acid. A strong acid would obviously be a much stronger acid than any of these guys. Speaking of strong acids, would we have Ka values for strong acids? Should we have Ka values for strong acids? The answer is no. And the reason is no, because a strong acid, like say hydrochloric acid, breaks apart into H plus and Cl minus. And since you have 100% of these guys here, there is no equilibrium. It's a one-way street. So for an equilibrium constant, you need an equilibrium. So sometimes people ask, how do I know it's a weak acid or a strong acid? Well, if you see a Ka value, it's definitely a weak acid. So that's a pretty big hint. You can find it on a Ka table. It's a weak acid. So you will never, ever see a strong acid have a Ka value. I would say the only strong acid that you probably would see on a Ka table is sulfuric acid, because it actually has two hydrogens to give. The first one is actually a strong acid. And the big value that they give you is usually will say large, which is not very helpful for the calculation. So that's really the only one that you will see kind of on the table. And usually it's the first one that says large. The second one that comes off there, you'll actually see a value. But other than that, that's a very good way to know you're dealing with a weak acid. Ka value only for weak acids. Strong acids don't set up an equilibrium, so they do not have a Ka value. Here are some Ka values from your table in your book. Here's acetic acid, which is a very common one we use a lot. Again, as we talked about here, here's arsenic acid. There's cyanic acid, carbonic acid. Now, here's some other ones here, formic acid. We have our oxalic acid. We'll look at this one here. We'll look at carbonic acid, which is right here, I think. So we'll look at carbonic acid. And the reason, again, as we might have talked about last time, but just in case we didn't, something like carbonic acid, which is a diprotic acid, has the ability to lose both hydrogens, but they do not come off one at a time. I think we talked about this when we were talking about sort of conjugate acid-base pairs. They do come off in a stepwise fashion. So something like carbonic acid, the first thing that would happen is the first H plus would come off, and you would be left with HCO3 minus. There actually is a Ka value associated for that process where it loses the first hydrogen. The next thing that would happen is the hydrogen carbonate would then lose another H plus, and that would leave us with our carbonate. And there's also another K value associated with just the second process that occurs. That is why when we add these together, we get the overall thing of it. It appears that the carbonic acid will drop off two hydrogens at once and make carbonate, but it actually is a stepwise fashion that it occurs. And that's why when you look at this table, like we just saw there, that does come from your book, you will see two K values, one for the first hydrogen that comes off, one for the second hydrogen that comes off, and you'll see actually two listed there, which is right here, I think. So this would be for the first hydrogen that comes off this value. This would be the Ka value for the second hydrogen that comes off. So with our diprotic acids, our triprotic acids like arsenic acid, this would be for the first hydrogen that comes off, second hydrogen comes off. and third hydrogen that comes off. Now, as we might have talked about, is it easier to remove the first hydrogen or the second hydrogen? Which one's easier? First hydrogen is easier. Once you remove that, it becomes something that is negatively charged, and it's going to hold on to that positive guy a little bit tighter. And we see that when we look at the values of K here. If we look at carbonic acid, for example, Ka1 is 10 to the minus 7. Ka2 is 10 to the minus 11. So as you can see, the K value actually starts to decrease. For every hydrogen that comes off, it gets much harder because we get a much smaller Ka value for the second hydrogen. That means for the second hydrogen, we mainly have reactants, which means not much of the H plus is coming off in that step. So it gets much, much harder as you keep trying to remove those hydrogens. Any questions on that there? And we also see that same trend here. That's like to the minus 3, to the minus 7, and then the last one is to the minus 12. What it virtually means, as we'll talk about, is for the most part, for diprotic acids, triprotic acids, most of the hydrogen comes off in the first step. It gets very, very difficult to remove the rest of the hydrogens. All right, so let's take a look at a problem like this, which is what is the pH of 0.5 molar HF, and we want to use a Ka value, so we'll use 6.4. Okay, so we'll use the Ka value that we see there on that table, which is slightly different, I think, but we'll use it. It is, where is it? We'll go with 6.4 to the minus 4. So the Ka value here, 6.4 times 10 to the minus 4 for HF. Now, because this is a weak acid, I recognize that HF is a weak acid, and I definitely see a Ka value. We need to do this basically as an ice table. So we will take our acid, which is a weak acid. We will write the dissociation equation. Once again, I'm just going to do the H plus and the F minus. If you want to do plus water and then the H3O plus on the other side, that's perfectly fine, because in the end, water is going to be left out anyway. So that's the deal on it. So if you want to leave it in an equation, it's fine. Just don't put any numbers there. We're going to do this just like a normalized table. We're given the concentration of our HF, which would be 0.5. This would be 0. This would be 0. The change here would be minus X plus X plus X, which means at equilibrium 0.5 minus X, X, and X. Do you have a K value on your paper? No? Okay, I just want to make sure. Otherwise, we would use that one. All right, so at this point, just like a normalized table, we're going to go into our equilibrium expression, which is our Ka. This is going to be H plus times F minus divided by HF, and that is going to equal, what did I have? It's at the minus 4, I think, right? 6.4 times 10 to the minus 4. We're going to take our equilibrium line here like normal and put it into our expression like we did with our equilibrium problems before. That's going to give us X squared 0.5 minus X is equal to 6.4 times 10 to the minus 4. The K value is large or small here? It is small, so I'm going to try and assume that X is equal to 0. And that means that I will get X squared divided by 0.5 equals 6.4 times 10 to the minus 4. I'm going to multiply this to the other side and also take the square root of it afterwards. So that would give me 6.4 to the minus 4 times 0.5. I then want to take the square root of it, and that gets me an X value of 1.789 times 10 to the minus 2. I do need to check my X value, right? And we check it by doing what? We take the X value and we divide it by what we were going to subtract it from. So in this case, we would take it divided by 0.5, times it by 100%. And if I do that and times it by 100 here, I end up with 3.6%, I think, which is less than 5%. So that is good in this case, yes. That means that in this particular case, unlike traditional equilibrium problems where we're interested in everybody's concentration, we're actually just interested in the pH, right? So in order to calculate the pH, we need what from the table? We need the H plus concentration, right? And we need the equilibrium H plus concentration, which in this case is equal to X. So in this case, X equals the H plus concentration from our table, which is 1.789 times 10 to the minus 2. That is what we need to calculate the pH, which would be minus the log of the H plus. Gives us minus the log of 1.789 times 10 to the minus 2. And here we go, log of 1.789 to the minus 2. Looks like we'll call it 1.75, we'll call it, I guess, a little bit on the rounding there. Would be my pH in this case. Any questions on any of those steps? Yes, sir. I'm sorry, say again. Well, we could do this one of two ways. We could either, if you're asking here for this part, we can either multiply everything to the other side, do the quadratic formula, which you can if you want. But because the equilibrium constant here is small, when the equilibrium constant is here is small, that means that you should mainly have reactants at equilibrium, which means not much is going to the product side. And by default, what that means is there's not a big change that's occurring. So every time we have a K value that's kind of on the small side, we could assume that X is equal to 0 because the change is not going to be very big. And that's why we solve it. But we do need to check it because it will not always work, and especially will not always work in these type of situations. So you do want to check it. And if it happened to be over 5%, then we would have had to go back and sort of solve it a different way. Other questions on that? Yes. Yeah, so you would only assume X is equal to 0 for anything that you were subtracting X from or adding X from. The reason we don't assume that this guy, for example, here is 0, that X, is frankly for two reasons. A, the logical reason is you have nothing to solve for at that point if you get rid of all the X's, right? But the real reason is F minus is starting with 0, right? And so really is H plus starting with 0 on the product side, which means anything that it gains is significant, right? If you have nothing and you gain like $1, that's a significant amount of money, right? Or if you gain 5 cents, it's more than what you started with. So there's a significant change that's occurring. When we look at HF in this case, it started with 0.5 in terms of its concentration. So whatever it sort of lost is going to be relatively insignificant. And that's why we get rid of anything that we're subtracting from or adding from. But really anything that starts with a 0, anything it gets is going to be significant. So you don't get rid of those X's. And the more logical answer is you would have nothing to solve for at that point. So you got to keep some X there to solve for. Other questions on that? All right, so just to show you again, if we have the exact same sort of setup, if we did our HF going to H plus and F minus, and instead of our 0.5 concentration, we had 0.05, which by the way, we probably should have rounded the pH to just 1 decimal place. There we go, plus X. This would all be the same basically, except that that is 0.05X, X and X. This would go into our expression here. And I think we were using, what we're using there, 6.4, I think, right? Yep, 6.4 times 10 to the minus 4. Now, if we were to sort of go and try to solve this here, Let's see how we did with that one there. Yeah, so in this case, if we went and solved for x and we assume that x is equal to 0, we would get x squared divided by 0.05 minus x is equal to, no, that would be gone, 6.4 times 10 to the minus 4. Taking 0.05 times 6.4 to the minus 4, taking the square root of it would give us an x value 5.657 times 10 to the minus 3. Now, when we divide it by 0.05 times it by 100, we end up with about 11%, right? Which is not good. Yeah. So you definitely want to make sure that you check it. It will not always work. Obviously, in this case, we would have to continue on and solve it a different way. So this is a good reminder that, it doesn't work in all cases. What is really the difference between those two cases? The first concentration was 0.5, right? The second concentration was 0.05. They kind of seem the same, but they're not, right? Which one is a larger concentration? The first one that we did, right? And we're okay on the assumption, right? The second one was a much smaller starting concentration, right? So if you think about like a pizza and you have a whole pizza and somebody takes one slice, not a big deal, right? There's still like almost a whole pizza left, right? But if your starting pizza was only 2 slices and somebody took 1 slice, that is a much bigger proportion of what you started with. So the concentration of your acid and even your base in these situations is important as to whether or not the assumption will work, because if you have a relatively good concentration to start with, the assumption probably will work. But if you're starting with something that's really small to begin with, a little change for something that's small is going to be a significant amount of change, and it might not be a good assumption in that case. So concentration really does play a role in whether or not sort of that assumption would work. So as we saw in this particular example that we did, when we're dealing with a weak acid, and really when we're dealing with a weak base as well, we approach them as equilibrium problems and we do ice tables. Really, one of the major differences is a lot of times we're not interested in everybody's concentration. We just want the H plus concentration to get us to the pH. And when we're doing bases or weak bases, we want the OH minus concentration to get us to POH. We will, in most cases in this class, ignore the auto-ionization of water. And what that means is this: there are some books and some examples where they'll go, well, just water by itself has a much higher H plus concentration than your acid or whatever it may be. So we'll just use water's concentration. So we're not going to do any of that here in this class. So pretty much if it says like 0.5 molar HCl or 0.5 molar HF, that is the only contribution of H plus is going to come from that weak acid. We won't think about any contribution from water itself. Just note that some books, I don't think the book we use does it, but some books will do that. They'll go, hey, this is a super small concentration of H plus from your acid. Really, water in there by itself has a much higher concentration. So we'll ignore the contribution of water. We use our ice tables, and again, our X will give us the H plus concentration, allows us to get to the pH at that point. All right, so why don't you give it a try here? What is the pH of a 0.122 molar monoprotic acid? Monoprotic means it gives one H plus away. HA is an example you could use for something like that. So monoprotic 1H plus, HA is an example of something you could use. All right, take a couple minutes there, calculate it up, see what you get. Look here, so again, this is a monoprotic acid, has 1H plus. By the way, if you had a diprotic acid and didn't have a formula, you could use H2A for diprotic and H3A for triprotic acid if you happen to have 3 hydrogens give off. Is there a difference in the charge of A in each of those? There is. This is -1, this is -2, and this is -3. So, you got to keep that in mind as well. In this case, we're doing monoprotic, so we'll do our HA as just a generic acid here, breaking apart into H plus and A minus. We initially have 0.122. We could safely assume 0 of these guys. Change would be minus X, giving us 0.122 minus X, X, and X. Any questions on the ICE table here? We're going to go into our Ka expression, which in this case is going to be H plus times A minus divided by HA. And that will equal our 5.7 times 10 to the minus 4. That will give us X squared divided by 0.122 minus X is equal to 5.7 times 10 to the minus 4 in this case. Once again, we do have a Ka value that's on the relatively small side, so we could assume X is equal to 0. Is it a good assumption? It is not. If you checked it, which you should have, it would give you like 6.8%, which means it's not such a good job on that side. So we do need to go back and solve it another way. So I'll just skip to that part there. We're going to multiply this to the other side. That will get us X squared is equal to, we got 0.122 times 5.7 to the minus 4. Going to give us something like 6.95 times 10 to the 5. And that will then be minus 5.7 times 10 to the minus 4x. We're going to bring everybody to the same side, giving us an X squared plus 5.7 times 10 to the minus 4x minus 6.95 times 10 to the minus 5 is equal to 0 in this case. This is going to go into our quadratic, right? So that is going to give us X is equal to minus B, 5.7 times 10 to the minus 4, plus or minus the square root. When you do the inside part of the square root, you end up with 0.002783, which you then would square root and get you, after you square root, 0.01668. That's all going to be divided by 2 times A, which in this case is 1. So that would be 2. This is going to give us our 2 answers. We'll do our minus 5.7 to the minus 4 plus 0.01668 divided by 2 gets us an X value of 0.008055. Or obviously here, the other one should get you a negative number, which should not be so good, I think. But just in case you want that negative number, negative 0.008625. This obviously cannot be the right answer because H plus is equal to X, so we cannot have a negative concentration. So that means that this number here on the left should be our H plus concentration. Will give us 0.008055 molar, geeking our pH minus the log of it. And to get us minus the log 0.008055, about a 2.09 on our pH in this case. Yeah. Any questions on that? Now, if you just blew through without checking, you get a pH of like 2.07, which, you know, is different. Yeah. So make sure you do check it. Any questions on any of those steps there? So again, a good reminder that, you know, take the second to check just to make sure. Yeah. It does also make sense. This is an acid and 2.09 is an acidic pH. So that all works out nicely there. Yeah. Once again, if for some reason you got a pH of 12, that is probably something wrong along the way in that calculation in this case. Any questions on this one here? All right, so let's try another one here. Calculate the H plus concentration. We'll also do the pH as well. Why not? Of a 0.010 cyanic acid. 6.2 times 10 to the minus 10 is the Ka value. I'm assuming maybe the right answer is up there. I would hope. Okay, let's take a look at this one here. So once again, if you weren't sure what type of acid this is, we do see a Ka value. So once again, that tells us it's a weak acid. It also should tell us we need to do an ice table here to solve for what we're looking for. So that is what we'll start with. We'll break it apart into H plus in this case and a little cyanide there, Cn minus. We're going to initially start with 0.01, 0 and 0. Change here, minus x plus x plus x means at equilibrium 0.01 minus x, x and x. Once again here, this will go into our Ka expression, which in this case is our H plus times our Cn minus divided by our HCN. And that obviously equals Ka value given to us. So putting that in gives us x squared divided by 0.01 minus x, 6.2 times 10 to the minus 10. Once again here, we could assume x is equal to 0 because of how small the Ka value is. That then gets us x squared divided by 0.01 is equal to 6.2 times 10 to the minus 10. We're going to multiply this to the other side and also square root it. And that will get us a little square root action maybe here. Can give us an x value of, we'll call it 2.5 times 10 minus 6 molar. Seeing it on the list here, so that looks good. We do want to check it though. So once again, we're going to check it by taking our x value we just got. We're going to divide it by the 0.01, which is what we were going to subtract it from. And we're going to times it by 100, and you're not even 1%. So you're like at 0.02%, which means this is good. That means that that should be the concentration there of our H plus. Also means we could get the pH, which I added on here, would be minus the log of 2.5 times 10 to the minus 6. And we'll do minus the log 2.5 to the minus 6. Looks like a 560 there. Still acidic, which is good. Any questions on either of their calculation? So Ka problems are really just equilibrium problems where we're really interested in the H plus concentration. We do all the same sort of things that we do with a regular equilibrium problem. If you can make an assumption, you could try it. If you don't want to do the assumption, you could still do the quadratic formula and solve it that way, whichever way you prefer there. Any questions on any of that there? Okay. So let's talk a little bit about percent ionization of an acid. The percent ionization of an acid is really the ionized acid concentration at equilibrium divided by the initial concentration. So it really is the H plus concentration that's floating there at equilibrium divided by the initial acid concentration times 100%. It is literally the check that we do. So that is literally how we do our check to see if our assumption is good, is really calculate the percent ionization. And basically, if it is ionized less than 5%, it's okay, our assumption in that particular case. Now, in a strong acid, it is 100% ionized, as you can see here. And for our weak acid, the percent ionization starts to decrease with increasing concentration of the acid. So that was sort of like my example earlier when I talked about sort of the pizza example. If you had a whole pizza and just took one slice out, not a big deal. You know, you still have a good amount still there. It's not really broken apart. But obviously, again, if you started with just 2 slices and somebody took one away, it is a bigger percentage. And that is sort of what we see here. As the concentration increases, what we lose is a lower percentage of H plus coming off, as opposed to if our initial concentration was really small, there's a big amount of ionization basically happening because we're pretty much starting with a much smaller amount than obviously our larger amount. So we can actually use something like percent ionization here to help us calculate things like the equilibrium constant expression. So if we took formic acid here and we actually want to calculate the Ka, we would take our formic acid, and we know it's a weak acid because we are looking for a Ka value. So that tells us it's obviously a weak acid. It will break apart into H plus and HCOOH minus. So we could do our ice table like normal. Initially here, we have 8 molar of this guy. We have 0 this guy, 0 this guy. Change would be minus X, and plus X, which means at equilibrium, 8 minus X, X, and X. Now, normally what we would do is take the Ka expression, which in this case would be our products, which is the H plus times the HCOO minus divided by HCOOH. And again, we're looking for that there. So there might be another piece of information that will help us get there. And it actually is the percent ionization information that's given to us. Here we are told that it is 0.47% ionized. So what we could do is use our percent ionization formula, which is the H plus concentration divided by the initial acid's concentration times 100%. And if it is 0.47% ionized, the H plus concentration, our initial concentration of our acid here was 8 molar times 100%. This is going to be helpful because this will allow us to solve for the H plus concentration, which if we go to our table is part of our table here. So let us do that. Let us solve for the H plus concentration. Would be 0.47% divided by 100% times 8 molar. And that would give you 0.0376 molar would be our H plus concentration. How is now knowing the H plus concentration at equilibrium going to help us calculate the Ka value? When we go to the ice table, right, at equilibrium, H plus equals X, right? And that X, is it different or the same as this X? Same. And is it different or same as this X? It is the same. So now that we know the H plus concentration, much like we talked about with lab today, we could actually use that as our X value because that's what H plus equals. And now we actually have the values that we need to calculate the Ka, pretty much identical to what you'll do in the experiment we did today. So what we would have basically is up on top for our Ka would be 0.0376 squared. On the bottom would be 8 minus 0.0376, which is our X value. And if we do all that good stuff there, that gets us 0.0376 squared divided by 8 minus 0.0376. Gets us a Ka value of 1.8 times 10 to the 1, 2, 3 minus 4. As our Ka value. So in this particular case, we're able to use the percent ionization given to us to basically get the H plus concentration at equilibrium. And from our ice table, we can see that that basically equals X. That allowed us to get the equilibrium concentrations of everybody else. And now that allowed us to actually calculate the Ka value. Any questions on that one there? Okay, so I think that's a good stopping point. So we'll stop there.